All right, this video is to go over the decibel scale, another one of the applications of logarithms that I teach in North Carolina Math 4. And again, the point of what I'm going to show you is how to determine how many more times and tenths one noise is than another noise. So this is going to be very similar to the Richter scale. There's just a slight difference to the formula. So the psychological sensation of loudness varies with the logarithm of the intensity, called the Weber-Fechner law or Fechner law. And so the intensity level measured in decibels is defined as beta is equal to 10 times the common logarithm of I divided by I sub 0. So that's our standard intensity. Where the they call it reference intensity. This should read 10 equals 10 raised to the negative 12 watts per meter squared at a frequency of 1000 hertz, which measures a sound that is just barely audible. And then we call that the threshold of hearing. And this is for somebody who has perfect hearing. They would be able to hear this. Now, like we saw in the Richter scale video, knowing I sub 0 and this 10 to the negative 12 really isn't necessary. All right, so let's take a look at an example of what you're going to see in class. So the intensity level of a normal conversation is 60 decibels, while the intensity level of a normal whisper is only 30 decibels. How many times more intense is a normal conversation than a whisper? Again, most people would initially say, well, it's twice as intense. However, the decibel scale, like the Richter scale, is a logarithmic scale. So we know it's not going to be as simple as just twice. So what we're going to do is we're going to figure out that difference in intensity. So we're going to come in here and I'm going to open another document because I'm probably not going to have room to show you all the work for this. So we're going to be looking at the intensity for a standard conversation at 60 dB. So that is going to be 60 dB minus that of a normal whisper. So we want to know how many more times intense is a normal conversation, 60, minus a normal whisper, 30. And like I did in the Richter scale video, we're going to call this noise number 1 and noise number 2, just to distinguish them because I'm going to have to use subscripts again. And so this is going to be equal to, now the big difference here between the Richter scale is, if you notice the decibel scale, deci is implying that there is a 10 in front of this. So we have 10 times the common log of the intensity of noise number 1, that is our normal conversation, divided by that threshold of hearing. And so this is representing the 60. And then I'm going to say minus 10 times this common logarithm of our intensity of our second noise. This is our common whisper, divided by the threshold of hearing, or the intensity of the threshold of hearing. All right, so at this point, I cannot use the quotient property like I did in the Richter scale, because both of these logarithms have a 10 in front of them. Now, there's a couple of options. I think the easiest option is to simply factor out that common term. So I'm going to have 10 times this common log of the intensity of that first noise, that is the common or the normal conversation, divided by the threshold, the intensity of the threshold of hearing, minus the common log of that intensity of that second noise, that is our normal whisper, divided by that intensity of the threshold of hearing. Now, what I'm going to have to do at this point is I could go ahead and, let's go ahead and use the quotient property for my logarithms and condense these logs into a single logarithm. So that will now give us 10. They do have the same base. Remember, that's important for the quotient property. So I'm going to say the common log of, and I can drop the parentheses off because now I only need to multiply it to a single logarithm rather than a or instead of two logarithms. And so now, using the quotient property, I've got to divide these two arguments. So I'm going to have the intensity of noise 1 divided by that intensity of the threshold of hearing, which is in turn going to be divided by the intensity of noise 2, which is divided by the intensity of the threshold of hearing. Now, those of you who have watched my Richter scale video, you kind of probably have an idea of what's going to happen next. But if you haven't, what you should see is that we're dividing one fraction by another fraction within this single logarithm. So when we divide fractions, remember that we multiply by the reciprocal of the denominator. So what's going to end up resulting here is I'm going to, instead of dividing, I'm going to multiply by the reciprocal of that denominator. And when this happens, that intensity of the threshold of hearing is going to simplify out, and we're simply going to be left with 10 times the common logarithm of intensity 1 divided by intensity 2. And this is actually, just like in the Richter scale video, this is what we're looking for. We want to know how many more times intense was the louder noise than the quieter noise. And so we're going to bring this back down. This is 60 decibels for our normal conversation minus 30 decibels for our normal whisper. We're going to continue solving from there. So 60 minus 30 is indeed 30, is equal to 10 times the common log of the quotient of the two noises, the intensity, I should say the quotient of the intensities of the two noises, which is what we're trying to get at. And that's what we want, because this is going to tell us how many times more intense noise 1 is than noise 2. But at this point, I cannot rewrite it as an exponential because my logarithm is not isolated. So I'm going to need to come in and divide both sides by 10. And that's going to leave us with that 3 is equal to this common log with the ratio of intensities, or quotient of intensities of our two noises. Now that that is isolated, now I can go ahead and rewrite this thing in exponential form. So since it was the common logarithm, it means we're going to have a base of 10. So I'm going to have 10 to the third power. And that is going to be equal to the argument from our logarithm. That is the ratio or quotient of the intensities. So all I need to do now is evaluate 10 to the third power, which turns out to be 1,000 in this case. And so what we have is that the intensity of that normal conversation, it turns out that it's about 1,000 times as intense as the rating for a normal whisper at 30 decibels. Okay? So remember when I said the average person would probably look at this problem and say twice, because 60 decibels is twice that of 30 decibels? Well, it turns out that's actually not the answer to this question. The normal conversation, or I should say the intensity of a normal conversation is about 1,000 times as intense as a normal whisper. Now, with that, we know that not all people converse at the same level, and not all people whisper at the same level. This is just saying for a normal conversation and a normal whisper. And that's how we compare two decibel levels and say how many more times intense one noise is than a second noise.